Hello, my name is Kevin Wilson, and I'll be presenting the paper Not Everything is Dark and Gloomy, a concentrated study on power grid protections against IoT demand attacks. We'll first start by acknowledging the authors of this paper and study. Bing Huang from the University of Texas, Alvaro Cardenas from the University of California, and Ross Baldrick from the University of Texas. This paper was presented at the Usenet Security Symposium in August of 2019, and the links below are to the paper itself and the PowerPoint presentation template provided by Georgia Tech. The objectives of this presentation can be summarized by the following list. First, we will give brief examples of cyber attacks against power systems. Then we will ask and answer what is a MadIoT attack and how is it performed. Then, we'll go over the current infrastructure's methodology to protect against MadIoT and attacks in general. Next, we'll give a summary of the paper's research of MadIoT attacks in small and large-scale systems. Then, we'll also summarize the conclusions of the paper, and then finally finish off with any future research that can be performed using MadIoT attacks as a subject. Attacks against power grids are nothing new and has been occurring since its creation. These started with physical attacks against substations, transmission lines, distribution lines, and other important components. Indirect attacks, such as theft of material, such as copper and other recyclable metals for money, and vandalism have all contributed to power outages in one form or another. The newest threat that is becoming an ever-growing concern and is on the rise are cyber attacks. Recent attacks have included the Ukraine power grid, which has been attacked several years in a row. This resulted in mass power outages with hundreds of thousands affected. Here in the United States, we've had many attacks over the years, with almost the same outcome. It is likely that many more incidents are occurring than are being reported. Known attacks against the energy sector often follow a pattern which generally does not produce immediately detectable consequences. The initial cyber attacks were either a DDoS, distributed denial of service attack, to block communication of the power grid infrastructure, spear phishing attacks or other social engineering techniques to gain access to critical systems, and illegal electronic entry to the SCADA, the Supervisory Control and Data Acquisition Center, which is the lifeline of most power grid systems. From there, the attacker could do almost whatever they wanted. Recent work and studies have proposed a novel form of attack called manipulation of demand via IoT, or MadIoT. It showed that if an attacker compromised hundreds of thousands of high-energy IoT devices, such as water heaters and air conditioners, the attacker could cause various problems to the power grid, and this includes frequency instabilities, line failures, and increased operating costs. This paper concentrates on the cyber attacks involving IoT devices and how MadIoT can affect power systems. As a reminder, IoT stands for Internet of Things, a system of interrelated computing devices, mechanical, and digital machines with the ability to transfer data over a network without requiring human-to-human or human-to-computer interaction. There are many IoT devices, but the ones we are focused on for this presentation are ones that can affect the power usage of a home. These include, but are not limited to, a smart fridge, smart doorbell, smart thermostats, and many other appliances that can be controlled by an internet interface. The vulnerability of IoT devices is a well-known problem. Previous work has demonstrated that devices from cameras to door locks can be compromised directly or through their designated smartphone application. A large-scale compromise of these devices can enable attackers to affect network infrastructures. What are the impacts of performing a MadIoT attack on a power grid system? Is it possible to take down the operations of a power grid? Unfortunately, from previous research and real-world attacks, the answer is yes, but it's not as easy as one might think. We will go into the details of what this attack does and the impacts it could potentially have. It has to be mentioned that the topic of MadIoT attacks has been researched before, but this paper has a different conclusion, and the reasons can be summarized as such. In previous research, there is no system-wide under-frequency load shedding, and this UFLS model will be discussed later in this presentation. So this meant all generators were tripped when the system frequency dropped. There was also no timing of protection in transmission lines, so all lines operating above the rating are also taken out. And finally, simulations in different timescales were separated. In this research, a detailed model of under-frequency load shedding is utilized to prevent generators from being disconnected from the grid too quickly. The timing of protections in transmission lines is modeled more accurately so that the lines are tripped in time inversely proportional to magnitude or overload. And on the converse, simulations in different timescales are coordinated. They are designed in a cascading outage analysis tool. There have to be certain assumptions made when conducting this study. Now, we all know what is said about assumptions, but it's actually necessary in order to help establish a baseline before the research is complete, and these will help explain the outcome. The first is that IoT attackers have the full and unlimited ability to control the compromised portion of loads. The second is the actions of attackers to increase or decrease the compromised loads are simultaneous. And lastly, third, is the portion of the system demand compromised by the cyber attackers are evenly distributed at each demand connection point in the transmission system. The third assumption is a speculation about the scalability of an IoT attack. For example, if the adversary is able to compromise one brand of air conditioner, they can systematically apply the attack to as many air conditioners as possible in the target system. So let's say if the total energy capacity of all such air conditioners is 10% of the system demand, this 10% of the demand is likely to be spread to every demand connection point in the transmission system. Now that we have everything established, how would a mad IoT attack be performed? There are two common scenarios that I'll cover, and the first is the one you might imagine during this presentation: overloading a transmission line. A line overload is the most straightforward attack and can be very effective. Once an attacker compromises the household IoT systems, they can start applying methods to increase electrical demand. This can be done a variety of ways. For example, if connected to the refrigerator, lowering the temperature of the main compartment and freezer. If linked to the home thermostat, increase or decreasing the temperature depending on the weather to activate the HVAC system. Whatever the method used, the home will then require more electricity, and the small changes may go unnoticed by the homeowner for quite some time. Instead of a gradual increase, the attacker may go for a shock attack and activate everything possible at once without care to the observations of the homeowner. So depending on the IoT setup of the household, all lights, kitchen appliances, etc. will activate at once to its maximum capacity. Many occurrences can accumulate into an overload of the transmission line. When this happens, the cables sag due to the nature of metals expanding when heated. Even though regulation requires at least 15 feet of clearance of most transmission lines, there is a possibility in some areas the lines will come into contact with trees or other objects, and when this happens, either the lines will fault or worse. When the line is taken out, the power originally handled by that line now goes to the neighboring transmission line, and the cycle will repeat itself where the line is overloaded and eventually taken out, although it might be faster because the load is now greater. This creates a cascading effect where almost every transmission line is going to be taken out. And finally, it accumulates to a blackout, the main purpose of the mad IoT attack. Now this covers a basic way that most might go about attacking a power grid system, but the next type of attack is a bit more complicated because it takes advantage of the setup of the power generators of a power grid system. This attack is called energy imbalance, and it's important to go over the current state of power system design, which can allow for this. To store electricity in the long term and in a large scale is currently not economically feasible. The technology is just not there yet. This means we have to match the demand by users with power generation in real time. This is accounted for by the design of electrical generators. An electrical generator consists of a stationary magnetic field, a stator, in which a rotating electromagnet, An armature spins to produce electrical current. Generators of this design used in power plants are enormous, and the mass of the armature is huge. When a demand is put on a generator, it cannot instantly increase their output to meet the demand due to the nature of its design and the mass of the armature. The generator will first reduce the speed of the armature to immediately convert the kinetic energy to the system in order to supply the electrical demand. The average speed of all generator units in the system is represented by system frequency. When the MadloT attack occurs, it will create a situation where there is more demand than generation in the system. As explained, the taxation on the system will start to lower the system frequency. But why is that bad? Generators have a threshold for operating frequency, a safe range in which they can operate. If they go beyond these limits, they will shut down to prevent permanent damage to the equipment and for other safety reasons. Since these electrical generators are very expensive items and integral to the system, this failsafe is required. This increased demand, accompanied by generators shutting down, is catastrophic to the power grid system and can lead to a blackout. Now that we see the different forms of incursions a MadloT attack can encompass, what are the current protections a power grid system have to defend against this? The first is over-under voltage protection. This covers the scenario when a voltage of a bus is too low or too high. A voltage relay will be triggered after a set amount of time. This activation time depends on an equation modeling configuration thresholds and over-under voltage relay pickup values. All of this is an effort to protect local components, that they don't allow their unit to operate outside the system frequency range of the system. So it will disconnect the units from the system to prevent damage. Next is the N-1 system, and this strategy is very common. It's applied to other system setups as well. For example, a RAID setup on a computer. Its principle is a system can lose any one of its end components, such as a generator or transmission lines, and continue to operate safely and serve power to customers in a large area. The next was mentioned in a previous slide, comparing past research to the current research done in this paper, and that is under-frequency load shedding. It is a countermeasure applied by bulk power system operators to reduce the incidence of generator under-frequency tripping, which is a great danger to the reliable operation of the power systems. UFLS for short is a coordinated disconnection of small and non-critical components to prevent a large blackout, but also accounts for some components which should be disconnected absolute last if at all, such as hospitals, police stations, and other critical services. All of this is a coordinated effort to uphold the standards of best industry practices, which is the protection of generators and overcurrent protection. Now, it's important to note, for day-to-day operations related to power grid failures, power operators focus on satisfying the N-1 criterion, as this is the most important failure condition that is regulated and enforced by most electric regulatory agencies. Large-scale events, such as a massive natural disaster, a terrorist attack, or even a cyber attack, have not been a major priority for industry practices because the likelihood of these events are very small, and investment in preparing for these events has higher costs than responding to them when they actually happen. Therefore, most of the industry efforts on cascading studies focus on smaller scale events that initiate a cascade, and also where the transient dynamics do not affect the cascade analysis too much. Because of this, a tool, the Cascading Outage Analysis Tool, or COAT, was designed by the authors of this paper and is used to produce the results of the research. It is used to study the power system reactions to large-scale disruptions. The COAT model considers both steady-state and transient stability analysis in different timescales, but coordinated so the transition of system stability from one steady-state operating point to another is present. The basic model checks for conditions that will trigger protective relays and assesses the time when relays will be triggered. Let's take a look at the scenarios performed for the research of this paper involving COAT and its results. The first was a small case study where a small system contains a minimal amount of generators, transmission lines, and the demand is not too taxing. Let's introduce an attacker who has infiltrated the system and increases the demand by 15%. It's identified a transmission line is overloaded. Now, that doesn't mean the line has been taken out yet or requires to be tripped, but it will exhibit the previously explained symptoms, such as the line will start to sag. To handle this overloaded transmission line, we must implement the time inverse protection scheme, which includes a time index that tells us how long we should wait until we take the transmission line out from the system, given the magnitude of the overload. If we take a look at the system frequency footprint of the system during the MadLT attack, in around 1 second, the demand is increased by 15%. If you recall in the previous slides regarding energy imbalance, more demand than generation in the system will cause the overall system frequency to drop. Under frequency load shedding is designed for the case when the system frequency goes down, and this will now activate. The system operator should also intervene by deliberately disconnecting load to help balance the system with the intent to bring back those disconnected loads online once the situation has normalized. In this scenario, the underload shedding has occurred twice, reducing the entire system load by 15%. Afterwards, the system eventually reaches a balance and becomes stable. Thanks to the actions of the underfrequency load shedding, the system load now is reduced to a level that no transmission line is overloaded, and thereby no line should be disconnected and no outage should be experienced. So what about large grid power systems? Well, in the upcoming examples, we're going to see a large North American regional study case which involves over 5,000 buses used. It's important to note that system protections are modeled in this research in a way that approximates the system response to the contingencies, but does not try to replicate the real protection configurations. This is because it's nearly impossible to replicate the actual protections, and is also not ethical. If this were an exact model, then the results can be used for malicious intent by wannabe attackers. In this scenario, we have an attacker controlling over 800,000 devices and increases the system load by 1%. This causes the system frequency to go down as expected, but notice the number is only by 0.2 Hz, a vast difference than in the small system scenario. In this situation, the large system is still stable. If we look at the power flow, it's the same situation, where nothing drastic is being changed. It's safe to say the protections are scaling with the size of the system appropriately. In the next scenario, let's say the attacker now has 10 times the amount of compromised devices, 8 million, and causes an increase of 10%. Now we see the system frequency goes down to a level where the under frequency load shedding will take over and correct the system, as we saw in the 1% scenario. As with the power output, there is a spike due to the attack, but again, it's quickly mitigated within seconds, thanks to the protections put in place to the power system. Previous research involving MadLT attacks painted a pretty dire picture. There are frequency instabilities, cascading line failures, and in the research scenarios, a 1% demand increase in the Polish power grid resulted in 263 line failures, and 86% of the load in the system was affected. It was also concluded that a 30% IoT demand increase attack would stop all the generators in the U.S. Western interconnection. It made it seem that we're just one major attack away from complete chaos. Because of the current in-place protection protocols, such as under-frequency load shedding and the N1 schema, the negative impact of MadLT attacks on the grid will not be as dire as originally thought. Hence the name of this paper, Not Everything is Dark and Gloomy. The results of this paper can be trusted because the authors put in comprehensive studies of power system stability under MadLT attacks, and they carefully developed and coordinated transient and steady state simulations. There are many challenges in the future involving MadLT device attacks due to the changing landscape of the power grid architecture. Renewable energy is becoming more prevalent and cheaper to implement. this type of energy generation is much different than the traditional devices. For example, solar energy does not have to deal with the heavy mass of an armature, as discussed previously. This means the system frequency can now change much faster, so new methods have to be developed to maintain the system frequency of the power grid. There are much more behind-meter distributed energy resources, which are setups such as rooftop solar. It's called behind-meter because the power grid system has no visibility to it. This gives challenges to proposed scenarios for research because load forecasts become much more difficult. If most users have solar, for example, when it's a sunny day, the load would theoretically be lower, and this has to be accounted for. Customers are much more electrically active and have devices which require more power. Tablets, phones, computers, and electric cars, to name a few. This can also affect projected forecasts. Finally, we assume the attacks happen when there is a demand. Given past experiences with real-world attacks, even though the attacker could not break into the SCADA system, the lifeline of the power grid system, other components were compromised, and this proved to have disastrous results. So, in coming to the conclusion of this presentation, we can conclude with these points. Our power and infrastructure systems need to account for attacks involving IoT devices, since it's becoming an ever-growing concern in the future and is currently happening. Even though it's not a big concern now, nothing is preventing it from becoming one. Research and changes are being made due to theorized scenarios, but it seems edge cases will have to be accounted for after the fact. It is impossible to account for every technological attack. Most changes in policy and standards are due to lessons learned. But don't let this worry you. Use IoT devices and don't let this presentation deter you from future use. If you want to have an IoT setup in your house, go ahead and get one. This presentation and the research of the paper is just to make you aware of what it could be used for. The Internet of Things is a new medium, and it is common with every new medium implemented that it could be used as a platform for malicious purposes. And we have to realize this can almost never be prevented. We should instead respect the power a new medium has and account for it accordingly. Thank you so much for taking the time to listen to my presentation. If you have any questions or comments, please post in the presentation thread.